Okay, well, good afternoon, everyone. Welcome to this afternoon's ARCHER2 webinar. It's my very great pleasure to welcome back Professor Timo Betcke. He presented a webinar for us a couple of years ago about Rust, which was extremely interesting and well received. And I'm looking forward to hearing his update this afternoon. Over to you,
All right,
Timo.
that's great. Thank you so much, Claire, and welcome everyone to the presentation. So first, a little disclaimer. I've got the presentation here on full screen right now, so I don't see any of the collaboration tools. So if there's anything wrong with the connection or anyone has questions, Claire, please just interrupt me because I don't see the needs of the collaboration. And yeah, so Claire mentioned already, I gave a couple of years ago already a seminar on Rust, an ARCHER2 webinar on Rust. And this year is it's also obviously involving Rust, but it's a bit different. This year is really not about introducing Rust or learning Rust itself, but it's really about implementing a large project with Rust. So, and our experience with this project and how we got everything onto ARCHER2 and some performance results and so on. So, and this is joint work with my good colleague Matthew Scroggs, who's at UCL Arc, Sri Kailasa, my former PhD student, who's now a postdoc in Cambridge, and Ignacio Fierro Picado, who is a postdoc with me. So from zero to ARCHER2 in 65,000 lines of Rust, and 65,000 lines of Rust, so it's pretty much roughly the amount of lines of code we have at the moment. And zero was really the start we had at the beginning. So we started this adventure 3 years ago, really with 0 lines of code and really virtually no Rust experience at all. And yeah, here we are, 65,000 lines of code later, still learning Rust. So, but we are quite happy to show that boundary element methods on ARCHER2. So, okay, I don't have to explain ARCHER2 here, the ARCHER2 webinar. This talk is, by the way, it's an extended version of a presentation I gave a couple of weeks ago at the SciMCC conference in Texas. So I gave a little bit of technical data on ARCHER2. But what we're going to talk about today, so the first part of the talk is going to be about the efficient distributed representation of Galerkin integral operators. And first of all, also defining what it actually is, because here I cannot assume that everybody just knows what we're doing. So it's a little bit about the background and the kind of computation simulations that we're interested in. Then we are going to talk about the Rust software components that we have developed over the project. So it was not just one big monolithic library, but we've developed a bunch of smaller libraries. And I'm not going to show everything out of those smaller libraries, but I'm going to show a couple of exemplary examples from this. So I'm going to talk a little bit about the kind of grid library that we were writing to illustrate the computation meshes. I'm going to talk a little bit about the linear algebra software that we were writing. And I'm going to talk a little bit about kernel evaluations, where we used lots and lots of manual SIMD code, which is obviously very important for HPC. We are going to talk about the MPI, about all of this and so on. And then finally, in the third part of the talk, we are going to move on to ARCHER2. And I want to show some ARCHER2 results. And the first part reason to show them is, first of all, to show, yes, we can do nice stuff on ARCHER2 with boundary element methods, which on its own is really interesting. I'm not really aware of many boundary element codes which are really large-scale scaling, and I'm not sure how much in the past was actually ever done on ARCHER2 in terms of boundary element methods. And the second part of the ARCHER2 results is really to demonstrate that Rust is ready for HPC. And we are also going to talk a little bit about deployment. I'm going to have some screenshots from our profile files on ARCHER2. I'm going to talk a little bit about Slurm files and kind of little stuff that we've been doing to get it to run on ARCHER2, which, well, hopefully not surprisingly, but actually at the end turned out to be very straightforward. So my that time PhD student Shrika Lassa, he spent some time, a couple of days, getting familiar with the ARCHER2 environment, and relatively reasonable time we brought everything onto ARCHER2. So yeah, but let's start with the first part, namely what we are really interested in. So the talk itself, or for the people in the audience who are not mathematicians, mathematical scientists, don't worry. It's we are not going to go deep into this. Talk is really computationally focused. Just want to show at the beginning very briefly the kind of equation we're actually working on. So we have a bounded surface gamma of, sorry, I'm saying here two-dimensional objects. It's actually a three-dimensional object, a two-dimensional surface in 3 dimensions. It's badly expressed. So, for example, the surface of a sphere. And then we want to solve a boundary integral equations, which is a typical form of a boundary integral equation is some integral over gamma of Green's function, g of xy, times phi of y ds of y equals some right hand f of x. And our task is we want to solve for this phi. That's a very typical task. And that's the most simple form of this. But if you draw down to more complex equations like computational electromagnetics with integral equations, or multi-equation systems, or you have composite material simulations, at the end, the individual components, they all essentially look like that. So the Green's function itself, with the general Green's function we're interested in, is of the form e to the ik abs of x minus y divided by 4 pi abs of x minus y. However, in this talk, we're always assuming k equals 0, so that we really have what we call the Laplace Green's function, which is just 1 over the distance of the points x and y scaled by 1 over 4 pi. Okay, so 1 over 4 pi is just a scaling factor. The important thing is 1 over the distance of the 2 points, which also means that the Green's function itself has a singularity when x and y are coming close together. So when we're integrating over the surface, x is a point of the surface, and we are evaluating singular integrals. We are integrating over the singularity. And this has consequences that we need to take into account in our codes. The applications of this is large-scale electrostatic computations. For example, we are doing some work on protein modeling, protein simulations, computational electromagnetics. We've done lots of work with the Met Office in terms of simulating atmospheric particles. So what happens when light is traveling through atmospheric particles? So what is actually radiated, what is reflected? So, and then we're looking at acoustic problems. So we had a larger project together with UCL Mechanical Engineering on high intensity focused ultrasound simulations in the lower abdomen of the human body. Fluid simulation is quite popular, not an area that I've myself worked very much in, but there are quite a few groups that are actually doing integral equations also for fluids. So lots of applications areas, and they're used a lot in practice. If you go to simulation companies, essentially anything that's computational electromagnetics or acoustics, actually industrial application, they will use boundary integral equation formulations. So yeah, so but how do we actually get this discretized? So what we use in our group is something that is called Galerkin discretizations. So in Galerkin discretization, the idea is you take your integral equation and you make it even more complex, namely you multiply with the test function psi, and then you integrate again. It's very similar to finite element method, where if you remember, if you have ever done finite elements, most simple way in finite element methods to get a discrete problem, you multiply your equation with the test function and you integrate. And you do the same here. The only difference is now that instead of one integral, you have 2 integrals. You have one integral that's coming from the integral equation over your trial function psi, over your trial function phi, and then now you have a second integral that comes from the testing together with the test function psi. And so your matrix that you're getting at the end, this is, you're getting out a discrete system Vx equals B. And the matrix V every element of the matrix is this double integral over the surface. And remember, each integral itself, because it's a two-dimensional surface, it's itself a two-dimensional integral. So this double integral is essentially, it's a four-dimensional integral, four-dimensional integration that you have here of the kernel function g of xy times your test function psi I of x times your trial function phi j of y ds of x ds of y. Okay, and in the most simple case, which is actually pretty good for lots of problems, your test and try function are just piecewise constants. Okay, there are certain problems where you don't even need continuity or smoothness, so you can just do piecewise constant test and try function, which means that the integral here over the surface gamma, they just drill down to integrals over single triangles. So you've got one test triangle together integrated with one trial triangle. Okay, and quite common is also just like in finite elements, these typical head functions, so that you have continuous piecewise linear test functions, and then again these integrals drill down to just the support of these functions, meaning you have a small number of triangles over which you're integrating for these test function. Also component-wise coming down to integrals of one triangle against each other, surface triangle against each other. And then correspondingly, the right-hand side B, that's just the integral of psi I of x, there should have been an f of x ds of x. Okay. In this talk, we are always assuming that we're using a surface triangulation. We are always using piecewise linear basis functions for all our numerical experiments here. Okay. To note here, what's really important is, first of all, these are non-local operators, meaning if I just discretize the whole thing naively, the whole matrix is dense, which means quadratic complexity for discretization and for matrix vector products. Now, we all know quadratic complexity that destroys our performance if you want to scale up to larger scale problems. So what is actually used in practice is certain tree-based methods that achieve linear complexity. So how do they essentially work? The kernel function g of xy. This in itself is, away from the singularity, is actually a smooth function. It can be represented by just a couple of terms of a Taylor series or some other low-rank expansion. And then if you can use that property to essentially, in a tree-like structure, recursively achieve a discretization that takes this low-rank structure into account. And via that, one can design methods which can assemble the whole thing approximately, so up to a certain accuracy, with linear complexity. One example of this type of methods is so-called fast multiple methods, and fast multiple methods are the object that we are going to use in this talk here. If you don't do this, then scaling the whole thing to supercomputer makes very little sense, because the quadratic complexity is always going to overwhelm you rather earlier than later. But if you're down to kind of fast multiple methods or related techniques, then you achieve linear scaling, and you can scale quite large. Okay, so and the picture I've shown here is actually from our work on protein simulations. So this is actually the molecular surface of Zika virus, and this is something, the underlying problem is a Poisson-Boltzmann problem, where we've been coupling an exterior modified Helmholtz equation with an interior Laplace equation. Okay. So what do we need to do to actually get discretize the whole thing? So when x and y are not close together, then we can use any kind of nice quadrature rules. So for example, a symmetric Gauss quadrature for triangles, or whatever we like to use. It just, everything is nice and smooth as long as x and y are not close together. So if we integrate over surface sets which are non-adjacent, we can just use any kind of standard triangle rules, and we can write this down. And then if you write this down into matrix form, we are getting an interesting construct, which is essentially can be written as a sparse matrix P transpose, say, and explain in a second what this is, times matrix G minus C times another matrix P. Now, what is all this? And that's going to be important for the ARCHER2 implementation later on. So the big G, this is just the matrix of all the Green's function interactions on quadrature points. So you take all the quadrature points that you have on your grid, so quadrature points in each triangle, and you take all the triangles, and you compute all the interaction in quadrature points. And that's the big dense matrix of the kernel function. That's a matrix we're never going to form explicitly because that's the one with the quadratic complexity. Then you need a correction because if I want to integrate over triangles who are close together, the singularity is hurting me. So I cannot just use the standard quadrature rule. I actually have to choose a different quadrature rule. We're going to do this on the next slide. So what we're doing is for triangles which are right next to each other, adjacent to each other, we're just subtracting out the corresponding interactions again. Why are we actually writing this in this funny form? This is so that the G matrix can be treated completely separated from the rest, because these are just point-to-point interactions of the Green's function. And for this, you can then use any kind of software that can actually compute these or allow fast computation of these particle interactions under the potential function. And then you don't have to worry for this about the grids or triangles or anything. That comes in through the corrections and through the P and P transpose matrices. So what are P and P transpose doing? They take our function space coefficients, so our test and trial function coefficients, and map them onto values onto the quadrature point. So the Pij, this is the value of my basis function on the quadrature points, multiplied with the integration element, which comes from mapping from a reference triangle to the physical surface, times the quadrature weight. So, and that's a very highly sparse matrix. So the P and P transpose, they have very sparse matrices. They're trivial to establish in parallel sparse matrices. C is also a very sparse matrix. However, because it subtracts out between neighboring triangles all the quadrature interactions again, even though it's sparse, because it consists of small blocks. These blocks take a lot of memory. So what you're doing in practice, we are not forming C, we are evaluating this directly. So it's kind of like a linear. It's a linear complexity operator that we never store explicitly. We are just evaluating this. And then G is the quadratic complexity bit. That's the one we are doing with the fast multiple library to bring the complexity down to linear scaling. Okay, so in our Rust implementation, we have to deal with these sparse matrices. We have to do something for the G. We have to do the corrections and so on. Okay. Now for the singular quadrature, at the end, we have to add on the correct quadrature rules for the nearby interactions, and we do this as well. There we use so-called fully numerical Erichsen-Sauter rules, and these are also highly sparse contributions, and these are pre-computed. So these are quite a lot of evaluations of the Green's function in individual triangles to get the singular quadrature correctly, but that's a pre-computation step that we're also doing. So later on in the numerical results, you will see the actual cost of this. It's a significant part of the setup cost, however, it parallelizes quite trivially. So this has very nice scaling properties. Okay, so then at the end, we have a fully discrete formulation. So we have our discrete integral operator V, which is now this P transpose G minus C times P plus S now, singular interactions. And I've given the form of the matrices. So S and P, these are sparse row distributed matrices. P transpose is assembled and distributed separately, so it's a transpose operator of P. G uses for its parallelization a locally refined distributed octree based on just the quadrature points, and C operates directly on distributed surface grid. So if you look at this, all of these matrices, they have different parallelization patterns, and we use individual parallelization patterns between all for each one of them, and then we vote on quite efficient library for ghost communicator and mapping between different parallelization layouts so that we can effectively and nicely handle this whole thing. Okay, so and yeah, that's essentially the formulation we want to bring into ARCHER2. And if you look at this, you have to deal with obviously we have to deal with the parallelization, we have to deal with the communication, but then we also have to evaluate the greens function interactions directly with each other. So that's for the correction matrix C. But then we also have the big fast multiple library underlying all of this. So there are quite a bit of components coming together here. And what I want to do in the next part of the talk is really talk a little bit about all the different software components. So the first part now, this was all not Rust at all. Any kind of programming language would be helpful for this. But for the second talk, we're now jumping into Rust, and we're going to talk directly about how we've done all of these things in Rust. And I'm not saying at all that this couldn't have been done in C, C++, or any other language. So, but I want to use the chance to highlight in this talk some of the nice advantages we have from working directly within Rust. Okay, so our software components that we've been using for this and the different library components. First of all, RST is the Rust Linear Solver Toolbox. That's a linear algebra library that we're developing ourselves. So I'm going to come to the topic of linear algebra in more detail. Then we have our high performance fast multiple library, which was Sri's PhD thesis. That's a very significant chunk. Then we have the direct greens functions interactions, point-to-point interactions of greens function, where we have, it's over 6,000 lines because it's a lot of manual SIMD which is in there for Intel and ARM architectures. I'm also going to comment on this. Then we developed our own grid, distributed grid library in Rust, which Matthew Scroggs, he's done a lot of work on this in order to distribute high order grids and high order basis functions. And then we've got our final assembly and evaluation routines, which does essentially this big chunk assembly of call the assembly for this matrix, for this operator, and put it all together. Okay, so we've got a corresponding paper in preparation, which is hopefully going to be finished next couple of weeks. Okay, so yeah, why Rust? Yeah, first of all, we all know, most people know right now this advertising blurb that it's a memory safe language design. That actually wasn't the most important aspect for this. Other things were more important for this because obviously something like memory safety is great for Google, Microsoft, and others when they're more and more replacing operating system components by Rust because it reduces vulnerabilities of their systems and saves them a lot of costs. But that's not really the main thing in HPC that we're having. So for us, first of all, in terms of the language, is the modern trade system. That's something I'm going to come to. And really, even more than this, a very modern tooling system in terms of compiler, package management, language server for development, document generation, unit testing, and so on. They all come together in terms of one package. So it's all, when you download Rust, you use it, you have it all together as one unified system, and they're all aware of each other, which is very beautiful in terms of development environment. Then obviously it uses LLVM, is very good, and there are some beautiful tools available, like for example, for people who've been using Julia, they're very useful is code inspection. What's actually the LLVM code look like of a function? You can do very easily the same in Rust, and you can see, oh, did my code actually auto-vectorize here, or did it not do this? So all of these things are very easy with the LLVM interaction. There's no runtime environment or garbage collection, so it's all bare metal code. Really, really nicely interoperable with C. Language complexity actually it's obviously higher than C, but it's less than C++. So Rust is a really smaller language than C++. Not necessarily an easier language, but definitely a smaller language. So our own experience in terms of these languages, so software development in Rust, definitely slower than Python. Before, we've done lots of Python over many years. But it's much, much faster than C++. And interestingly, I've also done a little bit of Julia over the last couple of months for another project, and my experience is at least as fast as Julia. So, and why is this the case? It's actually because Julia is supposed to be a very nice, easy language, and it is a beautiful, nice language. But the tooling system in Rust makes it so that when you're working in an editor that is language server enabled, it shows you essentially all the errors while you're writing. You can immediately correct them, and then you just compile at the end already correct code. It's a very, very smooth development process. Okay, so let's go into some actual examples from our project. So, and what I first want to show is Rust grids with anti-grid and the element. And the reason I want to show this is I can show off a little bit of traits. So so traits are like C++ concepts. They define properties that data types should implement. Okay, and so we have a pub trait grid, and this trait grid, it should have, well, it's an associated scalar type. Type T is a real scalar type. So real scalar again is a trait. So type T colon real scalar means this type T implements a trait real scalar, and this real scalar trait essentially defines what it means to be a real number to be able to work with. And then we have a type which is used as an identifier of different entity types. So we have a type entity for the grid, for the various cell types in the grid. And this, again, is derived from a trait or implements the trait entity. Okay. Then correspondingly, we have a geometry map type and so on, entity descriptor type, and various types of iterators. For example, here is the iterator over sub-entities. We've got other iterators as well, but I didn't want to show the whole trait system. So in this way, you can very nicely define what it actually means to be a grid in a very generic way. And the nice thing is, compared to, for example, in C++, if you were to look at traditional C++, you always have two options. You can do either runtime polymorphy or you can do static polymorphy. In runtime polymorphy, you would essentially do something similar here with abstract base classes, but then you always have to work with vtables and so on. You avoid this if you use static polymorphism, but then C++ templates, there's simple substitution mechanism. You only find out at the end via the compiler trying to compile everything together, did my types actually satisfy everything that I needed in the correct way? Now, traits, they solve this because everything that you do in Rust in terms of generics always needs to have, is always described by the traits that it actually needs to work. So you almost never see a piece of code where you just have a generic parameter without anything, because then you wouldn't be able to use it for anything. Rust always relies on you explicitly saying what traits does the generic parameter satisfy. And the whole language is built around this system. So you could say in C++, okay, since C++ 20, we also have concepts, but in C++, concepts and add-on in Rust, the whole language is designed around this system. That itself gives you a lot of power. And here is, so here on the left-hand side, I was just talking about types itself, types which are defined inside the grid trait, but obviously you can also do function and you can mix different stuff. For example, this own cell count function, this has a default implementation directly inside the trait, which you can overrule if you can either use, if you implement the trait for a specific type, you can either overrule this or with your own implementation or use the default implementation, or another function entity iter, which is just there, which just means needs to be implemented. Okay, and at the end, it's all static polymorphism, and it all gets resolved at compile time. So the contained objects, their types with lifetime bounded to the grid. Oh yeah, lifetime. I haven't really talked lifetime here. I just briefly mention this. If you go back here at the left, you have this type entity there, and then most of the code probably looks relatively familiar to other languages, but there's this kind of weird thing, this colon A there. Or this is prime A there, and that's a lifetime annotation. And lifetime annotations are something explicit lifetime annotations are something very specific to Rust. So what they allow you is to explicitly talk about lifetime relationships of objects. So for example, here, this type entity, this has a lifetime, which is called A. And then at the end, we have this funny thing is self colon, and then this prime A. And what this means is that self is the grid type, needs to live at least as long as the entity. And if you think about this, that makes sense, because if I have an entity inside the grid, the entity only makes sense as long as the grid itself is actually alive. So if I have the cell of a grid and the grid gets destroyed, then the cell doesn't make sense anymore. And that's essentially what it's saying. And using the system, we can actually design very complex lifetime relationships at compile time, so that the compiler for us can actually check these relationships. And that might seem infamous at first, and some people, they, especially beginning with Rust, sometimes bang their head against these lifetime management, especially when the compiler says complains about lifetimes not being satisfied. But it's a very powerful tool to have this temporary dependence between data types, which in other languages is very, very difficult to tell the compiler about. Okay. So then when we are talking about grids, obviously we need to work on grids, we need to distribute them. So we use MPI from this. And so I've done a little bit of a segue here to MPI. MPI, using MPI from Rust, fortunately very straightforward. There's a very mature RS MPI project, which is currently maintained by Jet Brown, who some people here might know from Betcke, his work in Betcke, who's at the University of Colorado, Boulder. And this provides a beautiful Rust native interface around all the low-level unsafe C language binding of the MPI functions. So these are safe Rust abstractions over the low-level C MPI, and it works really, really nicely, and it's very natively integrated into Rust. So here's, for example, an auto-LV example. I'm not going to go into details, but here this auto-LV, essentially what we are creating a send partition and a receive partition, which tells us which data goes where in terms of the auto-LV, and then we call the auto-LV with the send partition, receive partition. And one specific thing is, if you look at com.auto-LV count into, the second line from the last, there's this reference to send partition and then add mute reference to receive partition. So the add mute means mutable, so this is actually data that is going to be modified, while the send partition is not going to be modified. So that's again another thing that is very nice in Rust. It's explicit representation of things that are mutable and things that are not mutable. And by default in Rust, everything is not mutable. You have to explicitly annotate variables as mutable. Okay. Now to the core linear algebra. So linear algebra is quickly maturing in Rust. So we have three very popular packages. One is an algebra, which is general purpose linear algebra package and very popular also in the computational geometry community. Then there's ND array, which provides a low-level multi-dimensional array type similar to ND arrays in Python. And then there's also FIP, which is kind of like a Rust equivalent of LaPeX. So it provides Rust native linear algebra matrix decomposition is matrix multiplication with very high performance, very low level optimized, with no BLAST LaPeX dependency, and implements more and more dense and also more and more some sparse matrix decomposition in order to be able to create an environment for linear algebra where you don't have to explicitly link BLAST and LaPeX anymore. Now here in our code, we are still linking explicitly BLAST and LaPeX, but there's something that we might actually offer as an alternative for that. So, however, what we've been doing is we've been developing our own linear algebra core. And the reason for this is we wanted to have something that's specifically adapted to the needs of computational PD environments. So first thing we need there is the two different types of matrices are really important for us. Sometimes you want to have just large heap allocated matrices, lots of data, when you have some dense discretization or so, then obviously we have types to do this. But also when we, for example, have a hot for loop with some low-level operations in which we want to use matrices, then these should be stack allocated. For example, when you do some finite element matrices, have some small matrices that should be stack allocated in order not to have to work on the heap during a hot for loop. We want to be able to do this and do this in exactly in the same way as heap allocated matrices. Third thing, we really want to know explicitly about which routines allocate memory and which not. So we want to be very explicit to the user on this. And fourth, we want to really support distributed and parallel numerical linear algebra. So we've started developing our own library for this, the Ruskin New Software Toolbox, which is internally we're using it such in production and it's very robust already. We are spinning it's obviously it's available as its own GitHub project, but we are not yet advertising it very much to the community. Some people know about this, but it's slowly maturing to the way that we can have other people use it quite freely. So for example, things that you support is static lazy evaluation. So if you write 3 times one array minus another array, it doesn't create a bunch of temporaries. It never creates temporaries. It just does everything with lazy evaluation. And if you just say result.sum into and then array3.reference, then it actually is evaluating this. And the evaluation works in such a way that the iterators are done such a way there's just a single for loop at the end. There's no temporary variation. Then we've got a bunch of iterative solvers, more iterative solvers built on abstract operator interfaces. So we have traits that define abstract linear function spaces, and then iterative solvers based on these function spaces. And then whether you have a dense matrix, sparse matrix, whatever you like, you just wrap it in these abstract operator interfaces, can use the iterative solvers. We've got support for distributed sparse matrices, so which you can use, which is very robust and works very nicely, and a couple of other nice features like arbitrary n-dimensional arrays and compile time slices on them, current support for LAPACK functions. We have interfaces to MFPACK. Via the pipe library by Sarah El-Kastadi, we've got very nice SIMD support and other nice tools which are getting more and more robust. So yeah, so these are kind of the basic ways to that. So talked about the grid, I talked about the linear algebra. Now I want to talk about the Green's functions interactions themselves. And for the Green's function interactions themselves, the thing is this needs to be really, really fast because we need to do millions of those per second. So there we chose to go with very explicit SIMD implementations. And to implement those Green's functions, on the one hand, we want to support Intel AVX2, but also ARM Neon. And the way we do this, we always evaluate one X, so one target, against a number of sources, where the number of sources depends on the lanes. So if you're an AVX2 in single precision, you do 8 sources, same time in double precision 4 sources, corresponding to Neon 2 or 4 sources. And most critical operation for this is 1 over the square root, because you have 1 over the distance of points. So meaning distance always means a square root operation. So you have the 1 over square root, which you need to quickly evaluate. And that's a very known trick. Obviously goes back to into 1980s, 1990s. John Carmack's famous Doom trick about using Newton iterations for 1 over square root, and it's just a standard recommendation to do this fast. We do an approximation of the 1 over square root, and then we do a number of Newton iterations on top in SIMD. And the number of Newton iterations is 2 Newton iterations, single precision, 3 Newton iterations, and double precision on Neon. And an Intel AVX, we do 1 Newton iteration in single precision and 2 Newton iterations in double precision. And the way we tested this was just we tested a whole range of numbers and see that we got close to full precision on this, how many Newton iterations we needed to get this. And the way we implement this, so Rust itself supports low-level machine-dependent SIMD instructions. And Sarah El-Kastadi, she is in France. She has written a very nice library over it called Pipe, which supports hardware-independent SIMD routines, which are then mapped into machine-specific instruction depending on the architecture you're on. So there is also in the Rust standard library, there is also a development branch to develop hardware-independent SIMD directly as part of the Rust standard library, but this is not yet stabilized. So you need the nightly compiler for this, but the pipe library that gives you a way to do this in the Rust using stable Rust, so without relying on the nightly compiler. So that works very nicely. We can do very large evaluations with this. Here is the performance, for example, on single core, single threaded. We do on an M1 Pro. The AMD 3790X, that's a 32-core Threadripper, 2019 generation. So we do, for example, 20,000 points against 20,000 points, so quadratic complexity operations. We take 488 milliseconds on an M1 Pro on a single core, or 400 milliseconds on the Threadripper on a single core. Multi-threaded, obviously many cores of the Threadripper come in. Here we've gone even over to 500,000 points in reasonable time, 20 seconds on M1 Pro and just over 3 seconds on the Threadripper, which is pretty amazing in single precision. So, but the way we use this in practice, part of our big application, is that these operations which are done on single cores, and then threading is done higher up. Okay, so that's fine, and the corresponding library for this is called Green Kernels. Our low-level Rust library we were writing. For this library, this first library for which we've also created a stable C interface, and here you actually, in a Rust-based talk, you see some C code here. This is actually the C interface we've developed for the Green Kernels library. So if you decide to do a future project in Rust and want other people to use it, not everyone uses Rust, so it's actually very easy for a lot of problems to write simple C interfaces on top of the libraries. Yeah, and there's actually even very nice CMake integration available. So we provide for this Green Kernels library, because that's very useful for others, we provide a comprehensive C interface, including CMake support without problems. And if people integrate it into their C code, call the CMake itself just calls into the Rust build system, generates the shared library out of this, and just links it against the rest of the CMake stuff, fairly transparent to the user. Okay. The last big part is KIFMM, the kernel independent FMM method. Now this is huge, and in 2 or 3 minutes time for this, I can't really go into the details of this. We have so our FMM is based on the work by Lexing Ying on kernel independent buffer fast multiple algorithm 2 and 3 dimensions. It's a very classical, wonderful paper. And our paper of our Rust implementation, led by Sri Kailasa, that's currently it's submitted, it's currently in review, and essentially it's a kernel-independent FMM where we are representing a number of point charges inside an octree box by equivalence charges on the surface of the box, where the number of equivalent charges is independent from the number of charges you have actually in the interior. And this allows you to, because now the number of equivalent charges for each box is now independent of the actual physical charges, this allows you, using some recursive tree-based techniques and data compression, allows you to design a linear scaling algorithm. Okay, so I'm not going to go into details of this here, but there's lots of FT stuff and interesting tricks involved to make the whole thing fast and work nicely. So the performance we can compute using this library, we can compute on my M3 Max laptop. We can compute the interactions of 1 million points against each other for 3 digits accuracy in just 86 milliseconds. So that's fairly good. So point-to-point interactions, 1 million points, 1 million particles, 86 milliseconds. So that's very efficient. So that's uniformly distributed in the box. In the big table, I'm not going to get details of big tables, but FMM parameters are optimized for Threadripper. And the whole thing also works in parallel, MPI distributed. And MPI distributed, we're bringing this into this whole framework so that we not just do the point-to-point interactions, but we do a whole matrix chain with the P transpose G minus C times P plus the singular layer operator S to really do the whole integral operator in parallel. And that's where we're coming to the ARCHER2 results. So strong scaling results here look good as expected. So this is for the strong scaling. I went up to 8 nodes, and then KFM initialization time. So this here is 2 million elements, which leads to 12 million quadrature points. On 8 nodes is 2 seconds for the FMM initialization time. The singular assembly, the pre-computation of the singular integral is 5 seconds, and then applying the whole operator, the whole chain through is just over 1 second. which is very, very nice. We use on ARCHER2, we use per node, we use 32 MPI processes and 4 threads per MPI process. We also have weak scaling results. Careful here with the weak scaling results because we fix the FMM parameters for the highest number of elements. So they're really, really good just for the largest mesh, but it's really, really bad for the smaller mesh sizes. That's why the numbers here appear a little bit small there, but let's just focus a little bit slow there, but let's just appear on the highest results for which the parameters are optimized. So on 64 nodes, 140 million elements, and that's a very large-scale computation for boundary element methods. I'm trying to find papers where people are presenting larger computation, but it's mostly you find benchmark papers for FMM computation with particle interaction, but I haven't found large-scale benchmark papers so far for full integral operator evaluations. So that's what we can do, 140 million elements, and single layer operator apply time 9.2 seconds per operator. Or if we do the same up onto 128 nodes, 16,000 CPU cores, we get 6.7 seconds apply time. And this all with our complete Rust code. So using Rust on ARCHER2, let me just talk about this a little bit at the end. Okay, in hindsight, I'm saying surprisingly simple, but I remember when my PhD student Shri was getting our stuff in ARCHER2, he spent a couple of days saying curse words about the Cray compiler. We had a couple of issues with the Cray compiler and LLVM and Rust, so it all didn't work nicely together. At the end, we used the AMD optimizing C compiler, the AOCC environment, and with this everything worked perfectly, no issues with that. So we don't know what was going on with the Cray compiler, but just simply use the AOCC environment and everything is fine. So Rust is available either through spec or directly via rustup.rs. Rustup is the startup website for Rust. You can just download a small script there that installs a local Rust environment for you. That's the easiest way to get Rust. And we actually use this because in spec it always takes some time and the spec package is updated. And with Rust up here, a simple script that keeps the installation up to date. For Blast, we use OpenBlast from spec. And then that's really it. Apart from Blast, everything else is native Rust. So we are just doing our cargo build. Cargo is a Rust build system. We are saying cargo build and just download what it needs and just builds it on ARCHER2 without problems, as long as AOCC is implemented. And then we just pass the threading information as command line arguments to Rust. And inside Rust, we set the threading levels so that Rust doesn't try to spread out across all the CPU cores, and just uses the number of threads per MPI process that we wanted to assign, and that's really it. So our my .profile file on ARCHER2 is really just load spec, load the mpish environment. Then we're loading OpenBlast, and we are just setting the location for OpenBlast for the Rust flag. So Rust flags, that's a compile dependency for OpenBlast, put in there, and then we also put in the LD library path so that the shared object is found. And then we just this .cargoenv that just initializes Rust. And then in our Slurm files, which you see at the bottom, is also really everything is default and standard, just one-to-one copied from the documentation of ARCHER2. And the only thing that's different is then the srun command, where we are saying srun, and then we are just going into the project target release directory of Rust and say the script name of this. That's just default location of Rust binaries. If you have a project, then creates a target and a release directory. Everything else is fairly standard. That's really all you need, and that was all that was needed for us to get it onto ARCHER2. So yeah, is Rust really ready for HPC primetime? Yes, it is. Obviously, that's a very, very biased opinion from myself. Had we focused on Julia a few years ago, I probably would have given a talk now about Julia is ready for HPC primetime. But no, Rust really is ready. It was a very good experience for us. So it's great tooling, mature MPI interfaces, good SIMD support. these kind of things make a good choice for HPC. However, and now the big caveat, native GPU support is still early prototype stages in Rust. There are groups working on this, also from the Rust direct compiler team. There are people working with LLVM to allow prototype developments to compile kernels written in Rust directly into CUDA kernels. But why this is in principle working as prototype, it's still early stages, so early as alpha. If you talk to some Rust compiler developers, it will still take a little bit of time to get native GPU support. Until then, if you need GPUs, you have to link them in via C++ interfaces. That's a reality right now for GPU. And also, obviously, a compute library ecosystem not yet mature. So we've developed a lot of stuff ourselves that in C, C++, footage just use existing libraries for. Now, for us, it was part of the fun experience and giving back to the community and helping the community build up and contributing to a Rust HPC ecosystem. But obviously, if you just want to run your application, that's maybe not necessarily what you want to do, what you want to focus on. So, and also a small thing, Rust build system and spec do not yet interact very well. We would love to just provide a spec file for what we are doing, and just little issues there yet between Rust build system and spec. Would we actually do it again? Yes. Obviously also biased, but definitely yes from us. So what's really nice in Rust is the development speed in Rust is excellent and much better than C++, and that's a very significant factor. And none of the obstacles I've mentioned above have been very significant caveat for us, unless really you need comprehensive GPU support. I mean, you could say, hey, why did you spend so much time developing your own linear algebra stack? In principle, we could have just interfaced to PETC also from Rust. PETC is low-level C interfaces, but low-level C interfaces you can just call from Rust. But at the end, we wanted to run our own code and our own stuff for this. Okay, thanks a lot for your attendance. Yeah, and I'm happy to answer questions.
Thanks, Timo, for the talk. I see we have a few of you chats, so I will repeat them just so everyone can hear them. So we have a question from Sebastian, who asks, how faster was the Newton iteration implementation compared to using 1 over square root of x directly?
Oh, I don't have the precise data right now. We benchmark was internally at the time, I think it was a factor 2 or 3, but I can't give the numbers with guarantee right now. Need to re-benchmark. We are writing this stuff up as part paper. We are generating the tables. We need to rerun those benchmarks exactly. But when we tried initially, it was something I think factor 2 or 3 faster. Obviously, it depends also on number of assembly lanes and so on.
Thanks, Timo. Any other questions? Feel free to ask directly or to just write in the chat. Yeah. If not, I have a question. So how far did you compare computational kernel, like representative of the whole calculation between C and Rust? And did you see any difference in performance, like for vectorization or things like that?
I mean, we haven't done a C implementation of the whole library, so that's saying the previous implementation that we had, our previous generation software was single workstation code that used dense matrix implementation, and that for integral operators, and that was developed within OpenCL, using OpenCL, just-in-time compilation with OpenCL CPU drivers. So it was very different. But going back to that, because we ported those also over to Rust with Rust explicit SIMD, we had very similar speeds there. So in terms of just pure speed, if you have a very well-optimized C and C++ code, it will be as fast as well-optimized Rust code. I mean, at the end, it all goes down to LLVM, and if it all depends on does LLVM at the end generate decent code at the end. So there are not fundamental differences there, and no matter whether you write well-optimized Rust or well-optimized C++, I'm pretty sure you will get similar speeds at the end. There are certain things in terms of Rust, in terms of the way variables are by default non-mutable, and also the Rust memory model bans you from using aliasing and so on, where they're currently going on optimization within the LLVM compiler to make better use of this additional information that you have in Rust that you don't have in C. And there are speed advantages coming out in the future, but this is something where Rust compiler developers would be much more competent to answer.
Thanks, Timo. Any other questions? All right. So in that case, I think we can wrap up here. So thanks, Timo, for the talk. I think I've hit my head against trying to compile KFMM before on ARCHER2, so it's nice to see that you actually managed to run in that. So thank you, everyone.
Thanks very much, Timo.
Thanks.